So the first thing I want to start out with is talking about a continuous function assumes a maximum and a minimum value on any closed interval in its domain. That means that we are talking about intervals such as bracket 2, comma 5, meaning that you have an endpoint at 2 and 5. A critical point is something that we're going to be defining today, and it is where f of x is equal to 0. Let me rephrase that. F prime of x is equal to 0, or f prime of x does not exist. Those are the two things that we're going to be looking at for critical points. So critical points are simply spots where maxes and mins can occur. So notice that maximas and minimas, that's the plural for maxes and mins, occur at critical points, endpoints, and endpoints are critical points. Sorry about that. So if I look here, I have f prime of x does not exist because you have an endpoint, so it's a critical point. Notice how that does end up being a minimum. Then you have the first derivative is equal to 0 because you have the slope of the tangent line is equal to 0. Here you have the slope of the tangent line is equal to 0, so f prime is equal to 0. There you have a cusp, so the first derivative does not exist. There's another slope of the tangent line where the derivative equals 0. Here's another one where the slope of the tangent line equals 0, and then we have another endpoint. So in this picture, I have a minimum at the endpoint, a minimum here, and then I have maximums at an endpoint at this cusp and right here. And this is a critical point, but it doesn't end up being a max or a min. So critical points do not have to be maxes or mins. Looking at some of the words I've been using, extrema, when we're talking about extrema, means maximum and minimum values. Relative extrema is not the highest or the lowest value, but still a critical number. So going back to my last picture, this was the absolute minimum, and this was just a local or relative minimum. So the next word here is absolute extrema. That's the highest or lowest value of the function. So just like I showed you the local minimum, this is the absolute minimum, like I said, and this is like a relative max, and this is the absolute max. Absolute maxes and mins do not have to be the endpoints. It just happens to be in this particular problem. So this is the guidelines for finding those extrema on the closed intervals. What we're going to do is we're going to always check at the endpoints for maxes and mins, for those absolute maxes and mins, and we're going to also take the first derivative and figure out where it equals 0 or does not exist, because that's where the critical points will occur. So first of all, in some of your problems tonight, you're just going to see pictures. In the pictures, all you're asked to do is find the value of the derivative if it exists at the extrema. So we're simply going to be drawing tangent lines to the curves at those values. And as you can see, we have the derivative equaling 0 in this problem because the slope of the tangent line at that point is 0. However, down here, this is a corner, and so we know that the derivative of this point does not exist. Looking at some other types of problems, you'll see as far as directions are concerned, approximate the critical numbers of the function shown in the graph, determine whether the function has a relative max, minimum, an absolute max, absolute minimum, or none. So what I want to point out to you is, first of all, this does not have any endpoints, so we do not have to consider the endpoints. The only thing we're going to then look for is critical numbers. There is a critical number right here because the slope of the tangent line is equal to 0. However, it is not a max or a min, so there is no max or min for this problem. Excuse me. In this next problem, we have slopes of the tangent lines equaling 0 here and here, so at 3 and it looks like possibly 5. The endpoints again are not included, so those are not critical, or those are not going to be maxes or mins. This one, even though the derivative equals 0, is not a max or a min, but this one, the derivative does equal 0 here, and it happens to be the absolute maximum, and we can see that in the picture.
We're going to actually find the critical numbers not given a graph. We could also graph this on our graphing calculator to determine those critical numbers. But what do we do when we don't have a graphing calculator? Well, remember, we're supposed to find critical numbers at endpoints or where the derivative is equal to 0 or does not exist. In this case, we're not talking about closed intervals, so we will not check endpoints. We'll do that later in a couple problems. So what I'm going to do is I'm just going to go ahead and find this first derivative. I have to use the rules I learned in the last unit, which is, this is the quotient rule. So I need to do bottom times the derivative of the top minus the top times the derivative of the bottom, all over bottom squared. Now if you notice, what I did was to hopefully help me not have to write out things so many times. I did write bottom times the derivative of the top, but I put that top number out front because I knew I was going to have to distribute that through anyway. So my first derivative ends up looking like 4x squared plus 4 minus 8x squared. And I'll keep going here. If I do want to simplify this, negative 4x squared plus 4. And then on the bottom I have x squared plus 1 squared. So this is my derivative. Now I didn't just take a closer look at it. And what I'm going to ask myself is there anywhere where this derivative is going to equal 0 on the bottom? Because that means that the derivative would not exist if that was the case. So you always do need to check the bottom of the fraction to see if that is the case. This would yield the derivative not existing. But there are no values which will create 0 on the bottom, so I don't need to determine any critical points from there. The top, I now need to look at where does this derivative equal 0. This would actually yield derivatives equaling to 0. 0 on top and it gives you 0, and 0 on bottom is that does not exist. So what I'll do is I'll just take that top part, set it equal to 0, and solve. This will give me negative 4x squared. I could factor this as well, but I'll just solve for x squared. And I'll end up getting x is equal to plus or minus 1. Now, it did just ask me for the numbers, so I am going to be finished with that. Remember, critical numbers are the x values at which that occurs. The next example says locate the absolute extrema, so I'm only concerned with the absolute extrema on the function. And it is a closed interval. So I'm going to go ahead and start out by taking the derivative. So I can determine where it equals 0 or where it does not exist. Let's go ahead and take out a 3. And then let's factor that a little bit further. X minus 2x plus 2. So what does that mean? Well, it means at x equals 2 and x equals negative 2, those are critical numbers. It's where the derivative equals 0. Now, I am only talking about this particular interval, so I am going to cross out my negative 2 because it is not part of my interval. I am looking for the absolute extrema, so I need to test those values. I need to find out what is the y value, what is the height at 0. That's an endpoint. I've got to check this one for absolute max or min. What is the height at 2? Remember, I got that from the derivative being equal to 0, so it is a possible max or a possible min. And then the last one I need to check is at 4, because it is also an endpoint. Where do I get my y values? Well, I get my y values from plugging those back in to the original function. That means if I put 0 in for here and 0 in for here, I only get 0 for my height. When I plug in 2, I get 2 cubed, maybe I'll write that in red here, 2 cubed minus 12 times 2. Well, that is 8 minus 24, so that is a negative 16. And then when I plug in 4, I have 4 cubed minus 12 times 4. 4 cubed is 64 minus 48, which is a positive 16. So this happens to be my absolute minimum, and this happens to be my absolute maximum. It is because this is the lowest number, and this one is because it's the highest number. I have 3 more examples, and I'm determined to get through those here in the next video. So, in this one, locate the absolute extrema on the closed interval. So it's just like the last one we just did. I'm going to go ahead and find its derivative first, but before I find the derivative, I'll rewrite it. Please make sure that you are using proper notation when you're rewriting it. Now we're taking the derivative and denoting it as g prime of x. So I get 1/3 x to the negative 2/3. It's going to be a little bit difficult to think about, so what I'm going to do is rewrite it in terms of a fraction. And then I'm going to determine where does the derivative not exist or where is it equal to 0. Well, it's never going to equal 0 because I have a 1 on the top, but it will, the derivative does not exist. And where does it not exist at? Well, that would be at 0. So the derivative at 0 does not exist because it gives me 0 on the bottom of the fraction. So I need to determine where are those absolute extrema. I am looking at this interval, so 0 is within that interval. So I need to test the y value at -1, the y value at 0, and the y value at 1. What are those heights? Well, I will plug in -1 for my original, and I will get -1. I'll plug in 0, and I'll get 0, and I'll plug in 1 to get 1. So my absolute minimum is at -1, -1. My absolute maximum is at 1, 1. And that's just from this. This is the x value, this is the y value on us. This 0, 0 isn't anything but a critical point. The next one, in order to do this absolute value, we know absolute values make a v. So I need to know if that v, where that corner takes place, is within this interval. The best way to do this is just to strictly look at a graph. And I'm not even going to take the derivative of this function. I'm just going to look at a picture. The worst case worst, when we can't take the derivative of something, we need to just go ahead and sketch the graph of it. Well, what does this look like? I know that this value is telling me to move the graph up 3. And this minus in front of here is telling me that the v is upside down. And this one is telling me to move it 3 to the right. Using those rules from algebra, I can now determine that I have a graph that looks something like this. Now remember, we're only concerned about this closed interval. So I'll be checking the endpoints of -1, and I'll be checking the endpoints of 5 for absolute max and mins. But I also need to check this value, which is 3. When I plug in, and I can actually tell that there's a maximum right there at 3, and those other two have to be absolute minimums, but we'll go ahead and plug in those values. When you plug in -1 here, we get -1 minus 3, which would be a -4. Absolute value of 4 is 4, so 3 minus 4 is -1. When I plug in 3, 3 minus 3 is 0, 3 minus 0 is still 3, and I plug in 5, 5 minus 3 is 2, 3 minus 2 is 1. So what does this mean? Well, this one happens to be my absolute minimum. It's the smallest value. So I'll write that as -1. -1 is my absolute minimum. And then 3, 3 is my absolute maximum because it is the highest height. The 3 is the highest height. The last example of what I'm going to do is just take the derivative quickly. I may not get this finished. We can discuss this in time if I do not get it finished. So I've got bottom times derivative of the top, which would just be 1, minus top times derivative of the bottom all over bottom squared. When I go ahead and simplify this, I get t minus 2 minus t all over t minus 2 squared. Those cancel and I get -2 over t minus 2 squared. This is my derivative. The only critical number is right here at 2. So when t equals 2, there's a critical number. But look at my interval. This falls outside of my interval. Outside of interval. So I do not even have to check it. I only have to check my endpoint.